Alright everybody, welcome back to another calculus video. And in this video we are going to talk about kind of continuing that thread of integration. What is it? Why do we care about it? So at the very start of the class I said there were two main problems that kind of motivate all of calculus. One of those was the tangent line problem. Where we said, hey, given some sort of curve, find me the tangent line to the curve at that point, find an equation for that. And I'd say we've mastered that question, completely answered by the derivative. And then the other question we asked was, hey, what about the area under a curve, a general curve? Or you can extend this to what's the area of a general shape? So if I have some sort of curve between 2 points, A and B, how do I find this area under it? And we're finally prepared to answer this question. But to do so, we're going to have to take a little bit of a detour and talk about something called Riemann Sum, named after the mathematician Riemann, same guy behind the Riemann hypothesis, if any of you guys have heard of that. So, I say detour, it's not really a detour, this is kind of necessary build-up, but it's pretty technical, so don't worry. This is all of the stuff basically saying, hey, why are calculus tools going to work to answer this question? So, let's start with kind of a specific motivating example. Let's say we have the graph of f of x equal to 1 minus x squared between 0 and 1. So if we were to graph that, it would look like 1, 1, kind of like that, give or take. Maybe a bit more parabola and not less, and less circly. Anyways, we want to find this area. And the question is, well, how do we do it? There is no geometric formula that will give you this area, right? This is not a quarter circle, even if my drawing makes it look like that. So there is actually no geometry that will suffice for this. So we can't get an exact area using any technique that we've known so far. But using non-calculus methods, we can still approximate this area. And let me show you how. One thing we do know really well is how to calculate the area of a rectangle, or any shape that's made out of rectangles. We can get its area pretty easily. So what if I started saying, well, this is between 0 and 1. What if I started chopping this little interval into various sub-intervals? For instance, let's say I chopped it into two sub-intervals of equal width. So I'd have 0, then I'd have 1/2. Yeah, let's put it out there. Then we'd have 1. And let's say I drew rectangles now that get the height, their height from the curve, from my fx equals 1 minus x squared, and they get their width from the subintervals. So what do I mean by this? I mean, I'm going to say, hey, let's take the first rectangle, and we're going to draw its first corner there, extend it out to 1/2, and then draw down. And that's rectangle number 1. And then rectangle number 2, we're going to say, oh, that's the intersection of the line x equals 1/2 with the curve. And now I'm going to go straight from there, and then down to 1. Okay, well, let me shade the area of those rectangles in red. maybe I'll put the rectangles in red as well, so we can see them a little bit better. Okay, we very much can calculate that red area because it's just rectangles. What's their area? Length times width. And then I have two. Oh no, I add the two rectangle areas together to get my total area. Easily done. Right? But there's a problem. That red area definitely overshoots what we're going for. There's parts of the rectangles that are outside of this curve. So maybe not, right? For reference, I'm just gonna write this here. We're taking 0 to 1, and we're writing it as the union 0 to 1/2, union 1/2 to 1. Right? We're using this fact as we construct the rectangles. But what if I subdivided further? What if I did 4 rectangles instead of just 2? What would be different? Okay, well if I'm doing 4 rectangles instead of 2, we'd have 1/4, then 1/2, and then 3/4, and then 1. So here we're writing 0 to 1 as 0 to 1/4, and then 1/4 to 1/2, and then 1/2 to 3/4, and then 3/4 to 1. So that's what we're doing. We're subdividing 0, 1 into 4 equal subintervals. And if we did that with our given fx, what would happen? Well, okay, first rectangle, same idea, but it only travels out to 1/4. Let me make this curve a little more dramatic so we can see it a bit better. So we have that rectangle, red. Okay, then how about our next rectangle? Our next rectangle would say, okay, you're going to make your point right here, stretch out to 1/2, then go down. Then same thing. The height of the rectangle is the intersection of x equals 1/2 with our graph. 3/4, and then same thing right here. So we still have some amount of overshoot, but in general, it looks like that overshoot is getting a little bit smaller. So what is the area of each of those two examples? Well, because the heights of these rectangles are defined from the curve, this f of x, we can actually write their areas pretty easily. So here, the red area is the area of rectangle 1 plus the area of rectangle 2. What's the height of the area of rectangle 1? Well, it's my function at 0. How wide is it? It's 1/2 wide. How about this one? This rectangle has the height, the intersection of line x equals 1/2 with my curve, so it has height f of 1/2 times 1/2. And you're welcome to compute that as an actual number using this function. Go ahead, you just plug in 0 and plug in 1. But I'm trying to step away from that for now and move to more general what's going on. How about this red area? Well, now we have 4 rectangles, each with width 1/4, and their heights are going to be also given by the curve. So we're going to have f of 0 times 1/4. That's this first rectangle. F of 0 times 1/4. How about the second rectangle? F of 1/4 times 1/4. How about the third rectangle? f of 1/2 times 1/4. And finally, f of 3/4 times 1/4. So again, both overshoot the area, but this one looks like it overshoots a little bit less. Let me draw out an example with more rectangles to give this slightly more of a picture. Let's see here. Yeah, let's do n equals 8. So this is the case where if we let n be the number of rectangles we're dividing into, this is the case n equals 2, and this is the case n equals 4. 2 rectangles, 4 rectangles. What if I put 8 rectangles? It's one of those times when being a better artist would be very helpful for my teaching, but unfortunately it's just simply not the case. Okay, if we subdivide into 8 rectangles, we'd have 1/8, 2/8, which is 1/4, 3/8, 1/2, 5/8, 6/8, which is 3/4. This is 4/8, which is 1/2. And then we'd have 7/8, and then we'd have 1. So drawing my variable curve, we'd see I'm just going to draw the rectangles, not the shaded area. We have that rectangle, that rectangle, that rectangle, that one. So maybe it wasn't quite clear with the difference between n equals 2 and n equals 4, but we can very clearly see that between n equals 4 and n equals 8, the amount of area under the rectangles is getting much, much closer to the area under the curve. Alright, so the approximation gets better as n grows. What about for a different function? Does this same thing happen? Let's try maybe x squared. And for the sake of simplicity, let's say we're again going between 0 and 1. And let's sketch out the same 3 cases. So n equals 2, 4, and 8. So if we're looking at x squared between 0 and 1, what does that look like? That looks roughly like that. Okay? So now my rectangles would be, okay, so that rectangle seems to be kind of flat. How about this one? There. And this is all the area we have, rather than the entire area under the curve, which is much, much larger. So this one seems to undershoot. Okay, but that's only n equals 2. Let's draw more rectangles and see what happens. So maybe if we did 1/4, 1/2, 3/4, and 1. Someday I'll get better at art, but that's not today. Okay, so between 0 and 1 with 4 rectangles, what goes on? Well, we're still going to have our flat one right there, right? Because that is f of 0 is 0, or g of 0 is 0. Then we have our next rectangle, looks like this. We have a rectangle that goes there, and we'll have a rectangle that goes there. So again, another undershoot, but we got more of this area. And if we were to write out what the actual areas would be, let me put those up in the top corner. The actual red area here would be, okay, I understand that this rectangle is 0 area, but for the sake of argument, let's write it out as g of 0 times 1/2 plus g of 1/2 times 1/2. And g of 0 is just 0, so that's why we end up with a flat rectangle right there. How about over here? The red area would be g of 0 times 1/4 plus g of 1/4 times 1/4 plus g of 1/2 times 1/4 plus g of 3/4 times 1/4. Because we're, again, choosing the left endpoint of each rectangle to be intersecting with our curve. And we're undershoot. Okay. Well, what about n equals 8? And again, I won't bother writing out the actual area for this one, but I'll just draw a picture so we can see what's going on. All right, between there and there, if we draw our rectangles, we get something that looks like this. So we're missing barely any of the actual area under the curve at this point, right? At just n equals 8. So theoretically, if we kept adding more and more rectangles, our undershoot in this case and our overshoot for the other function would get smaller and smaller and smaller, giving us better and better approximations of the actual area under the curve. So let's look at kind of a general function. In general, you might have some undershoot and some overshoot. So let's say we had a function that looked something like that. And let's say we're working between here and here, A and B, whatever those things might be. And let's say we divide into some odd amount of rectangles. Say rectangle here, 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 here. So all with equal length. And if we draw our sum, we'd get something like So again, I'm using the exact same technique where I'm saying, oh, the height of the rectangle is given by the curve using the left endpoint. And then the width of the rectangle is just whatever width I've chopped up my interval into. And we see we get some undershoot, some overshoot. But hopefully we can agree that as the number of rectangles gets larger and larger, the amount of error in either way would start going down. So how can we quantify that general case? And then where does calculus come in? Since so far all we've been doing is geometry. So, the general idea for approximating and again, this is all kind of technical. Don't worry as much about all the technicalities of this, but it is kind of necessary build-up to see where this all comes from, because otherwise I'm just dumping some random stuff on you. Okay, so to generally approximate, we divide the closed interval from A to B into n equal length subintervals. So here we divided 0, 1 into 8 equal length subintervals. Here we divided A to B into 1, 2, 3, 4, 5, 6 equal subintervals. So n is some variable number. And what will their length be? Well, if they're all equal and they add up to make this interval, how long is this interval? Well, that interval is b over a, or sorry, b minus a long, right? 0 to 1 is 1 minus 0. A to b, it's b minus a long. Divide by n. And we're going to call that quantity, b minus a divided by n, delta x. So they all have this same delta x length. And now we pick representatives from each subinterval. So let's say we have representatives x1 through xn. So we have x1, x2, all the way to xn from each subinterval. You can almost think of those like test points from each one of these little chunks. Now, some of the most common choices of these quote-unquote test points are the left endpoints of the interval, which would be these. That's actually the one we've been using this entire time, is the left endpoint. That's one of the most common choices. The other common choice would be using the right endpoint. So that would be like here, 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 and here instead. Just shifts it over a little bit. Anyways, but you can pick any representatives you want from each subinterval to get n rectangles, and we're going to say that rectangle K, so K could be like the third rectangle, has height f of x sub k. So you're going to take your representative point from the interval and you're going to give that rectangle the proper height, matching it with where it is on the functions graph. And with delta x. So the same width that we computed earlier. Okay? Well, if you do this, the total area of the rectangles that you add up together? The total area would be f of x1 times delta x, so that's your first rectangle's area, plus f of x2 times delta x, which is your second rectangle's area, plus yada, 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 all the way to your nth rectangle's area. It's very common to write this kind of sum using what's known as sigma notation, which, yeah, if you don't like sigma notation, don't worry about it. I'm not going to bring it up again, except when writing these notes. Won't test you on it. But it's just common practice to write it this way, so you should probably see it. We write this as capital sigma, so this is the Greek letter sigma. Technically, it should have those little bars in it. And we put k equal to 1 to n of f of x sub k delta x. And you might be like, well, what the hell does all this mean? In general, if you have some sequence of numbers, a1, a2, a3, the sequence k equals 1, or the sum k equals 1n, ak, is a1 plus a2 plus an. So this notation, this sigma notation, just says, hey, add up each one of these things as k goes from 1 to n. So here we're saying, okay, add as k goes to 1 from 1 to n, f of xk delta x. And that will be precisely this thing. So, I know this is all technical. Bear with me for just a little bit longer. We're going to make a definition. Given this situation, so where we've divided our interval up like this, everything like that, given that situation, the sum from 1 to n, k equals 1n, of f of x sub k delta x is called a Riemann sum. Your book doesn't use the sigma notation at all, which is why I'm bringing it in here. But it's a good place to look if you're confused about all the technicalities of this. The book has it all laid out very nicely. But yeah, so it's called a Riemann sum, and this is essentially a good approximation for the area under the curve, because you're just adding together all the little rectangles that kind of measure it. So there's going to be some overshoot, some undershoot, but in general, pretty good approximation, and it gets better and better the bigger and bigger n gets. Okay, well, what if I wanted n to get really big? Like really, really big. Here comes the calculus. We can take a limit. So if I want not just an approximation, but the actual area under the curve, you can think of it as saying, I want, instead of a bunch of rectangles with some sort of overshoot and some amount of undershoot, I want those rectangles to get infinitely close together, infinitely thin, and thereby measure this more properly. So how do we do that? Let f be a non-negative. So non-negative means it's just greater than or equal to 0. Continuous function on the interval a to b. The area of the region under the graph of f and because f is always greater than 0, it makes sense to talk about under as below, right? Because if f were to cross the axis, then how do I make sense of that? We will deal with that though. So the region under the graph of f is the limit as n goes to infinity of the sum from k equals 1 to n of f of x of k delta x, where we have this kind of situation going on. These x sub k's are going to be our representatives. So they're arbitrary points. In the n subintervals of a to b. And each subinterval has equal with delta x, which is equal to b minus a divided by n. All right, so how does this all fit into what we want? Well, we're measuring the height of the curve here using any choice of test points we want. We're making the amount of rectangles grow because n is growing, and delta x, we're dividing by n, which means that this delta x gets smaller and smaller and smaller, the bigger and bigger that n gets. So this, hopefully I've convinced you, is the proper formula to measure what we want, so long as f is non-negative and continuous. You break either of those conditions and things can not necessarily do, but can start going wrong. But the most cool thing about it is as long as you do have these two conditions, it doesn't actually matter what choice you make for these x1 through xn's. So for instance, let's say we have some curve and I divide it into 4 regions. Maybe my first x1 I choose here. And maybe x2, I say, oh, I want x2 to be this endpoint. And maybe x3, I say, well, what about here? And x4, I say here. Well, then my situation with the Riemann sum in this case would be, that's my height, and that's my rectangle. So it's the entire width, but it's using this point as the height. Maybe I'll put a dash line there. Then this one would say, oh, go up to here, use that as your height. How about this one? This one would say go up to here and use that as your height for that entire region. And this one would say go up to here and do that. So even if I don't have a systematic way of choosing where my test points are, the cool thing is this limit will still be the same value no matter what. And that's kind of nifty. But it's not true in general. As soon as you break either one of those conditions, something can go wrong. So let's wrap this all up into a little bow and put some calculus on it, more than the limit. So, what if we have some random function that is neither continuous or non-negative? let f be any function, as long as it's defined on that whole interval. If the limit if our normal Riemann sum limit exists, right, because limits don't always exist, if the limit exists and has that property of it being equal for any choices of x1 through xk. So basically any function where it doesn't have to be continuous, it doesn't have to be non-negative, but it still satisfies that same nice property as you get for free if you have non-negative and continuous. If it still satisfies that, we call it the definite integral of f from A to B, and we write integral sign from A to B of f of x dx. So it's just like normal integrals, except you put a little a and the b at the end, and you write it as that limit. So this is our new symbol for this limit. All right, so some kind of factors of this definition, because it's a complicated one. A is called the lower limit of integration. And B is called the upper limit of integration. Alright, so that makes sense. We go from A to B. A is smaller than B, so it makes sense, lower and upper. Cool. Sticking with you there. Still confused about all that, but sticking with you on at least these names. So, if this definition confuses you, that's okay. This is real technical, and we will not use this definition ever to compute an integral. Why? Because this definition bloody sucks. You have to choose arbitrary points, and you have to prove that the limit exists and is equal no matter what you choose. It's a mess. They make you do it in some higher math courses. Math 412 and 413 are the ones at Cal Poly that handle this topic more rigorously. That's a mess. It's an absolute mess to try and use this definition. So in the next video, we're going to come up with a way to steer us away from having to use all this. But this is the kind of grunt work that builds up to getting this and saying, hey, this is the quantity we're going to be wanting to examine. Let's go from there now. A couple key points as well. The notation will make sense once you see the next video, but for now it might be a little bit confusing. This is a number. This is the area under the curve, assuming everything works out properly, which means it has to be a numerical value, right? Area is a number. Normal integral, or rather indefinite integral, antiderivative, is a family of functions. And it's going to turn out that there's a connection between these two things, and that's going to be known as the fundamental theorem of calculus. And that's kind of the whole build-up for this. So, quick definition. If this integral, definite integral, exists, we say f is Riemann integrable. On this integral. Or sometimes you'll just drop the Riemann and say it's just integrable. So a couple more points for this video, and then we can move on to the next one where everything will make a little bit more sense. Natural question, is every function integrable? Sad answer is no. For instance, I can define a really nasty function. Let's call it I. By I being 1 for x in the rational numbers, intersect 0 to 1, and 0 otherwise. And if you graph I between 0 and 1, well, it's a theorem of real analysis that anytime you pick 2 points on a number line, there's always a rational number between them. So this function, if you were to try to graph it, you can't. It would look like a bunch of dots up there and a bunch of dots down there. And it turns out that if you really play with the limit definition of the Riemann integral, it's impossible to put any sort of meaningful area under this curve. You get confused between whether it should be area 0 or area 1. In short, this is not Riemann integral. Don't worry about it. So the Riemann integral has some shortcomings. There's a way to step around that and define what's known as the Lebesgue integral, but that's a 500 level math class, and so we ain't even going to talk about that. Except I just did. So the question becomes, which functions are integrable? And I'm going to state a weak theorem that gives some amount of classification for that. Let f be any continuous function on a to b. Then f is Riemann integrable. On a to b. Right? Or in other words, what does it mean to be integral? It means that the integral from a to b of f of x dx exists. So, for any nice function, continuous is a pretty nice property for a function to have. The Riemann integral will exist and everything sorts out nicely. You don't need to prove this, you don't need to know why it works, it's complicated. So what does this allow us to do? it means that we can start quantifying the area under a curve for various functions. I'll use this space to draw the pictures. If we have a function that is non-negative between a and b, then the definite integral is truly the area under the curve. So you have this area A. It is directly true that A is the integral from A to B of f of x dx. But the definite integral, maybe it's kind of a misnomer to call it the area under the curve. It might be better to call it the net area under the curve, because if you have a function that strays between above and below the x-axis, maybe you have something that does that, and that's your A and your B. Well, if you try to take the area under the curve, right, it would split into kind of three categories. So you have this part, and this part. But these rectangles here would have negative height if you're trying to do your Riemann Sum rectangles. And the integral notices that difference. So in this case, if we called those A1, A2, and A3, is that visible on the video? Yeah, that's good. So if we call those A1, A2, and A3, then the integral from A to B of, let's say that's f of x, and let's call this g of x. The integral from A to B of g of x dx would be, in this case, A1 minus A2 plus A3. So it keeps track of the sign of the area. So, in general, integral is the net area under the curve. In practice, trying to compute these with just the definition is really bad. So we're going to go to the next video and develop something much, much better. I'll see you guys then.